These are Chapter 14, Notes 1, and we're covering inference for linear regression today. First thing we're going to have you do is we're going to have you go to page 786 in your textbook, and we're going to have you read problem 14.1. On part A, there is a number of things that we are supposed to do, including graphing a scatter plot, calculating correlation, and calculating the least squares regression equation, and answering a question. What I'd like you to do is take a look at problem 14.1, pause the video, answer the questions, draw the graph, and we'll take a look at your answers in just a moment. So once we've entered the data into your calculator, we can obviously go to second y equals in your stat plot. We're going to make a graph of a scatter plot, and if I do zoom 9, zoom stat, I should get a nice illustration of that scatter plot. We can figure out the correlation by going to stat calc. Remember, we use number 8, the linear regression a plus bx feature, and you'll notice that we get a R value of 0.994. That's your correlation. Our least squares regression equation also comes from the same screen, and this y hat equals negative 3.66 plus 1.197x. Do you think that femur length will allow a good prediction of humerus length? Based on the way the points look, I think it's a pretty nice looking scatter plot. It appears pretty linear. I think this is a yes. Now, in AP Stats, we work with numbers that meet one of two criteria. They're either parameters, which are numbers that describe the population, or they're statistics, which are numbers that describe the sample. Remember, parameters starts with P, population starts with P, statistics starts with S, sample starts with S. Easy way to keep them straight. Now, some examples of parameters and statistics you're familiar with would include means. If we're talking about the mean of a population, we use mu. If we're talking about the mean of a sample, we use x bar. Same idea for proportions. P is the proportion for a population, P hat is the proportion for a sample. Now in this unit, we're going to be working with the least squares regression line. You're probably familiar with the equation that's at the bottom that I'm going to put a little star next to, y hat equals a plus bx. This is based on data that was collected from a sample. Now, if we know the true total data set for the population, we're going to end up with a different least squares regression equation, which is mu sub y equals alpha plus beta times x. The y-intercept, we use the Greek letter alpha instead of the lowercase a. For the slope, we use the lowercase Greek letter beta instead of the lowercase b. And if we're talking about the standard deviation or standard error of our line, we're going to use s to deal with statistical data, or sigma to deal with data from a population. Now, if we take a sample of data and graph it, let's say we have this big set of population data, and we're just going to take a sample of that data and graph it. What you might end up with is any one of these slightly different sample graphs. A lot of these graphs are kind of similar. Maybe you get one graph that does this because maybe the points that you pick, maybe there's like 3 points, they don't line up like this. Maybe you have a little bit steeper graph. A lot of these graphs are pretty similar to each other, but based on the points you choose, you may get something slightly different each time. Now, if we could gather the entire population and graph it, our population line might look similar to this dark line here. Now, what I've done is I've overlaid all 5 of these sample graphs here, 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 and here, because what I want you to notice is that a lot of times the population data graph might be pretty similar to each of these little sample graphs. It might be kind of a nice little average of things. So this population graph right here, this one that's in bold here, would have the equation that I'm circling. Mu sub y equals alpha plus beta times x. So what do the values in this equation stand for? Mu sub y stands for the mean response. We're using it in place of y hat. Based on all of the x and y data points, it's what you get on average when you plug in a certain x. So if we plug in 4 for x, mu sub y is what we get on average for y. Alpha is the y-intercept of the population least squares regression line. It's approximately equal to a. To interpret it, we would substitute the context of what x and y are in the context of the problem, and we would say when x equals 0, the mean y value equals alpha. Other variables. Beta is the slope of the population least squares regression line. I have a typo in my worksheet. It's approximately equal to B. Beta is obviously the second letter of the Greek alphabet, so it should be replacing the second letter of our alphabet. To interpret this, what we would say is that the mean y value increases by beta for every increase in x of 1 unit. Again, replace the x and y with context in the example. Sigma is not in this equation. Sigma stands for the standard deviation of responses, or y values, about the population least squares regression line. It's a typical distance that each point is away from the line vertically. It's approximately equal to s. So you can sort of think of the standard deviation as being how far a point commonly is from the line in the vertical direction. So if you're measuring straight up and down, what's a typical distance that these points are from the line vertically? S is the standard error about the sample least squares regression line. Now S is not part of this equation, but I did mention that sigma is approximately equal to S. To calculate S, you're going to take the square root of 1 over n minus 2 times the square root of the residuals squared. Armed with this information, what I'd like you to do is I'd like you to move on to problem 14.1 part B, where you're asked to explain in words what the slope of the true regression line says about the Archaeopteryx. And then there's a couple other questions to answer as well. So pause the video, write down your answers, and we'll see what you get in just a minute. So we're going to use the script that we have for beta above here. So when we explain in words what the slope means, it means that the mean y value, in this case y is the humerus length, increases by whatever beta is, about 1.197, for every increase in axis femur length of 1 centimeter. Beta is approximately equal to lowercase b, which was 1.197, and our estimate of alpha in this problem would be negative 3.66. Now you should be able to go on and move on to number 3. Explain in words what alpha means in the context of this example. So we're going to use the alpha explanation, and we're going to replace x with the x variable, which again is femur length. The mean y was humerus length, equals alpha, which is approximately equal to a, which was negative 3.66. So that's our interpretation. Again, sometimes alpha doesn't always make sense due to extrapolation. Obviously, femur length is going to be a negative value. Based on our data, obviously, we're going to have to restrict our domain. And finally, the last problem we're going to look at is 14.1c. It says calculate the residuals for the 5 data points. We're going to do this by putting the values in list 1 and list 2 in our calculator, which we've done already. We're going to do the lin-reg step, which we've done already. And now we can put the residuals in list 3 of your calculator, which we'll do right now. Remember, you can highlight L3, go to your list menu, second stat, and you should find residuals among the names of the different lists that you might have here. We're going to put these values on your paper, and we're going to check that their sum is equal to 0. So what I'd like you to do is I'd like you to copy down those numbers. We'll take a brief pause, and then we'll reconvene and we'll finish the rest of this worksheet in just a minute. So I've copied down my residuals. When I added these numbers in my calculator, I got 1e negative 4. Remember, that's like 1 times 10 to the negative 4th power, which is the same thing as 0.0001. So basically, with a little bit of round off error, we're fine. The last thing we have to do is use the residuals to estimate the standard deviation sigma in the regression model. So what we're going to do here is we're going to crunch out a little formula. Now we know in this problem that our sample size n is equal to 5. So we're going to have the square root of 1 over 5 minus 2 times the sum of the residuals squared. Now we already have our residuals in list 3 in your calculator. To square the residuals, let's highlight L4, and I'm going to do L3 squared. This gives me my residuals squared. To take the sum of these residuals, what you can do is you can access your list menu, second stat, and we're going to take the sum of the numbers that were in list 4. These were the squared residuals. And here I got about 11.7853. So that's the sum of my residuals squared. It's the residuals squared added together. And that gives you 11.8753. I'm going to take this number, I'm going to multiply it by 1 over 5 minus 2, that's like 1/3. And then we're going to square root that number. And this answer of 1.98 is our estimate for sigma, which is also what S is actually equal to. And what that allows us to say is that S is an unbiased estimator of sigma. S gives you a pretty good estimate of what we think sigma is actually equal to.